Hello everyone and welcome back to yet another video of the organic chemistry series, and in this lesson we'll be doing amines, that is the 13th chapter. For the ones who are new here, we do NCERT and every single line of it in the least possible time, so you can watch your videos on the go. So this can serve as an audiobook as well as an NCERT highlight. So let's begin. Amines constitute an important class of organic compounds derived by replacing one or more hydrogen atoms of ammonia molecule by alkyl or aryl groups. In nature, they occur among proteins, vitamins, alkaloids, and hormones. Synthetic examples include polymers, dyestuffs, and drugs. Two biologically active compounds, namely adrenaline and ephedrine, both containing secondary amino group, are used to increase blood pressure. Novocaine, a synthetic amino compound, is used as an anesthetic in dentistry. Benadryl, a well-known antihistaminic drug, also contains tertiary amino group. Quaternary ammonium salts are used as surfactants. Diazonium salts are intermediates in the preparation of a variety of aromatic compounds, including dyes. In this unit, you learn about amines and diazonium salts. So basically, amines हमें मिलते कहाँ से? We have an ammonia molecule. We'll replace one hydrogen by alkyl or aryl groups, and you'll get amine. So in the first introductory paragraph, they're only giving you all the various possibilities of finding amines in daily life. You can have an anesthetics, you can have drugs also, antihistaminics, and the other biologically active compounds. So beginning with the lesson, we are given amines first. They can be considered as derivatives of ammonia only, obtained by the replacement of one, two, or all the three hydrogen atoms. So you can have primary, secondary, tertiary amines, depending upon how many hydrogens of the ammonia group have been replaced. And what is the structure? Like ammonia only, nitrogen atoms of amines is trivalent and carries an unshared pair of electrons, the lone pair that the nitrogen always has. Apart from that, it has three bond electrons as well. So nitrogen orbitals in amines are therefore sp3 hybridized, and the geometry of amines is pyramidal. Each of the three sp3 hybridized orbitals of nitrogen overlap with orbitals of hydrogen or carbon depending upon the composition of the amines. तो यहाँ पे तीन groups बन सकते हैं in a pyramidal shape. Fine, and this will be our lone pair containing lobe. So you can have different groups over here based upon what the composition of the amine is basically. So the fourth orbital of nitrogen in all amines contains an unshared pair of electrons, this one. Due to the presence of unshared pair of electron, the angle CNE, so this is the CNE electron, where E or C or H is less than 109.5 degree. For instance, it's 108 in case of trimethyl amine. So if you have trimethyl amine, so this will be 108, जो tetrahedral angle होता है. Classification: amines are classified as primary, secondary, or tertiary, again depending upon the number of hydrogen atoms which are replaced by the alkyl or aryl groups in ammonia molecule. If one hydrogen atom of ammonia is replaced by R, any alkyl group or aryl group, we get RNH2 or ARNH2, a primary amine. Then if two hydrogen atoms of ammonia are replaced, we get RNH2 and replaced by another alkyl or aryl group R dash. So you'll get RNH R dash, which will be a secondary amine. So basically primary में one hydrogen replaced RNH2, secondary में two of the hydrogens replaced, so you have R dash, and in tertiary all the three hydrogens are replaced of ammonia and you get R dash and R double dash. That's what it's trying to say: primary, secondary, and tertiary amines. Amines are said to be mixed. Simple when all the alkyl or aryl groups are the same, and they're said to be mixed when they're different. Very easy. Simple means जिनमें एक ही किस्म के groups होंगे, and mixed means different groups. Nomenclature: in common system, an aliphatic amine is named by prefixing alkyl group to amine, that is alkyl amine, as one word. Example: methylamine. In secondary and tertiary amines, when two or more groups are the same, the prefix di or tri is appended before the name of alkyl group. In IUPAC, amines are named as alkanamines. Very easy. So you have any alkyl group and you attach it to the amine and you say alkanamine. This will be the IUPAC name. For common system, you will have the alkyl group first and then you will join the amine at the end. So methylamine is common name, but if you go for methanamine, that is the IUPAC name जो यहाँ लिखा हुआ है, by replacing the E of alkane by the word amine. For example, CH3NH2 is named as methanamine. If it was methylamine, then it was the common name. In case more than one amino group is present at different positions in the parent chain. Their positions are specified by giving numbers to the carbon atoms bearing NH2 groups, such as di, tri, etc. We've done this in nomenclature, is attached to the amine. The letter E of the suffix of the hydrocarbon part is retained. For example, this is named as ethane 1,2-diamine. If you have more than one amine group, the E will be retained and you will name the diamine as such. After numbering, in aryl amines, NH2 group is directly attached to the benzene ring. So C6H5NH2 is the simplest example of aryl amine. In common system, it is known as aniline. Aniline is nothing but its aminobenzene. It is also an accepted IUPAC name. So aniline can be used. You can expect a question from here also. While naming aryl amines according to IUPAC system, suffix E of arene is replaced by amine. So C6H5NH2 will be benzene amine. In case of IUPAC, benzene amine. So पहले हमारा alkane का नाम आएगा, or whatever, say in this case it's an aryl group, you will replace the E by amine. So common and IUPAC names are given in the table. You can just go through the table. Ethylamine, ethanamine. Propylamine, amine, propane, 1-amine. So similarly. And then aniline or benzene amine. Both will be correct. Alright, you can just go through this table on your own then. We have preparation of amines, reduction of nitro compounds. All the nitro compounds, NO2 containing compounds, you can convert them into amines very, very easily. And how is that possible? Nitro compounds are reduced by reduction to amines by passing hydrogen gas in the presence of finely divided nickel, palladium or platinum, and also by reduction with metals in acidic medium. So what you do basically is catalytic hydrogenation, and you reduce the nitro compounds into amino compounds, into amines. So nitroalkanes also can also be similarly reduced to the corresponding alkanamine. So you can have over here H2PD, ethanol, or even metal in presence of an alcoholic medium, acidic medium. You can get this nitro group converted or oxidized into, reduced into the amine group. Reduction with iron, scrap and hydrochloric acid is preferred because FeCl2 formed gets hydrolyzed to release hydrochloric acid during the reaction. Thus only a small amount of hydrochloric acid is required to initiate the reaction. So you can use FeCl in a better sense because this HCl at the end it can be hydrolyzed. This FeCl2 that will be formed in the reaction, subsequently it will get hydrolyzed to HCl during the reaction, so you don't have to keep on adding HCl. Alright, so this is a better process. Then you have a monolysis of alkyl halides. You take an alkyl halide RX, you ammonolyze it. What do you mean by that? You have read that the carbon halogen bond in alkyl or benzyl halides can be easily cleaved by a nucleophile because there's electronegativity difference over here, right? Hence an alkyl or benzyl halide can be, alright, an alkyl or benzyl halide on reaction with an ethanolic solution of ammonia undergoes nucleophilic substitution reaction in which the halogen atom is replaced by an amino group. This process of cleavage of the CX bond by ammonia molecule is known as ammonolysis. What is ammonolysis? Cleavage of the RX bond with the help of a nucleophile, which is basically your ammonia over here. The reaction is carried out in a sealed tube. The primary amine thus obtained behaves as a nucleophile and can further react with alkyl halide to form secondary and tertiary amines and finally quaternary ammonium salt. So now this substituted ammonium salt, eventually this is what you get. अगर आपने closed tube लिया है, then the primary amine जो आपको यहाँ से मिलेगा, it again behaves as a nucleophile which will again be attacking this RX, and again secondary and then tertiary, finally you will get a quaternary ammonium salt. Alright. The free amine can be obtained from the ammonium salt by treatment with a strong base. तो इस salt जो आपको मिला उसको आप base के साथ react करवाएं, आपको आपका free amine फिर से मिल जाएगा. Ammonolysis has the advantage of yielding a mixture of primary, secondary and tertiary amines and also a quaternary ammonium salt. However, primary amine is obtained as a major product by taking large excess of ammonia. The order of reactivity of halides with amines is Ri, RBr and RCl. So Ri will be the most reactive in case it's ammonolysis. So basically you're trying to get ammonia as a nucleophile which is going to cleave the RX bond, which is already having a sufficient amount of electronegativity difference. Now we have reduction of nitriles, another method of preparation. What is now nitriles? We know C triple bond N containing compounds are nitriles. On reduction with lithium aluminium hydride LiAlH4 or catalytic hydrogenation, again H2PD and stuff, produce primary amines. This reaction is used for ascent of amines series, that is for preparation of amines containing one carbon atom more than the starting amine. So basically when you go up, when you ascend the amine series, what you have to do is you have to add on, keep on adding a carbon atom. So if you have 2 carbon atoms in the reactant side, you will have 3 from the product side. That's what it's trying to say. So whenever you reduce this nitrile in presence of whatever reducing agent you're taking or catalytic hydrogenation, what you get is a primary amine with a carbon number more than that of the reactant. Then you have reduction of amides. Acid amides, we know, C double bond O NH2. The amides, again you'll reduce them and you will get in the presence of lithium aluminium hydride, LiLH4 is very strong reducing agent, you will get amines from here also. Then you have Gabriel thalamide synthesis, very important. Gabriel synthesis is used for the preparation of primary amines. Thalamide on treatment, this is thalamide, just look at the structure of thalamide first. This is on treatment with ethanolic potassium hydroxide, you're taking KOH, a base, alright, it will form potassium salt. Okay, this H is going to get out, this will have a negative charge, and this K positive from here is going to attack, and you will get a salt. Fine, potassium salt you got. Alright, of thalamide only, which on heating with alkyl halide followed by alkaline hydrolysis produces the corresponding primary amine. So then you make it to react with RX, the alkyl halide. What happens from there is you will get potassium halide back as the byproduct, and this K will be replaced by the R over here. Fine, this will again be positive, this will be negative. So then afterwards, what are you doing to this? This alkyl thalamide, this will be made to react with an alkaline base, aqueous alkaline solution, and on hydrolysis it will yield the primary amine, and this structure will remain as it is as a byproduct. So this Na positive is going to react over here, and this R is going to come out, and NH2 will be reacting with it. So that is 1 degree amine or primary amine, that's how you get it. Now we have Hofmann-bromamide degradation reaction, another important reaction. Hofmann developed a method for preparation of primary amines by treating an amide with bromine in an aqueous or ethanolic solution of sodium hydroxide. So you can take sodium hydroxide. If you make this amide to react with bromine, you will get an amine. In this degradation, migration of an alkyl or aryl group takes place from carbonyl carbon. So this will be replaced. Alright, there will be a migration of the alkyl or aryl group, whatever is taken in the reactant side, of the amide to the nitrogen atom. Fine, this will come here. This is the migration. Fine, the amine so formed contains 1 carbon less than that present in the amide. So this is also something you have to remember. Now moving on, we have physical properties. The lower aliphatic amines are gases with fishy odor. Primary amines with 3 or more carbon atoms are liquid, and still higher ones are solid. Aniline and other aryl amines are usually colorless but get colored on storage due to atmospheric oxidation. Lower aliphatic amines, जिनके numbers जो है वो कम होंगे, are soluble in water because they can form hydrogen bonds with water molecules. So the lower amines, they can be soluble, they can form hydrogen bonds. However, solubility will decrease with increase in the molar mass of amines due to increase in size of the hydrophobic alkyl part. So since this again a hydrocarbon, what happens? The hydrophobic alkyl part increases with increase in the chain size, and as a result solubility decreases as mass increases. Higher amines are essentially insoluble in water. Considering the electronegativity of nitrogen of amine and oxygen of alcohol, which is 3.0, 3.5, you can predict the pattern of solubility of amines in alcohol in water. Out of butane 1-ol and butane 1-amine, which one will be more soluble? Amines are soluble in organic solvents like alcohol, ether, and benzene. You may remember that alcohols are more polar than amines form stronger intermolecular hydrogen bonds than amines. So they are more soluble. The alcohols become more soluble because there's large electronegativity difference over there. Primary and secondary amines are engaged in intermolecular association due to hydrogen bonding between nitrogen of one and hydrogen of another molecule. So basically primary, secondary amines intermolecular association bhi karte hain because there is hydrogen bonding between nitrogen of one and hydrogen of another molecule. Fine. This intermolecular association is more in primary amines than in secondary ones, as there are 2 hydrogen atoms available for hydrogen bond formation in the primary ones. Fine. Tertiary amines do not have intermolecular association because there is no hydrogen. You have taken out all the hydrogens in case of tertiary amines. Therefore, the order of boiling points of isomeric amines is as follows. So what can you say about the boiling points? Primary ka sabse zyada, then secondary, and then tertiary. This is something you have to remember. So this is about the boiling points. Intermolecular hydrogen bonding in primary amines is shown as this. Because there is a lot of hydrogen bonding, there's a lot of branching over here. You can see the boiling point of primary amines will be more than secondary than tertiary, because as soon as you go up higher this series, primary, secondary, tertiary, the number of hydrogen atoms decreases. As a result, intermolecular hydrogen bonding will decrease. So this table is giving you an idea about the molar mass along with the boiling points in Kelvin. Now coming to chemical reactions. Difference in electronegativity between nitrogen and hydrogen atoms and the presence of unshared pair of electrons over the nitrogen atom makes amines reactive, because this electronegativity difference 1, and the second very important, there's a lone pair present on the nitrogen of amines. The number of hydrogen atoms attached to the nitrogen atom also decide the course of reaction of amines. That is why primary, secondary and tertiary differ in many reactions, because obviously number of hydrogens depicts a large number of reactions as well. Moreover, amines behave as nucleophiles. Due to the presence of unshared electron pair, they can donate a lone pair, so they can behave as nucleophiles. Some of the reactions of amines are described below. So this was just the general characteristics. हम किन basis पे इनके chemical reaction study करने वाले हैं, based upon the lone pair, based upon the nucleophilic part of the compound of the amine, and also primary, secondary and tertiary differing in their chemical reactions. Now basic character of amines. Very easy. Now what do the bases do? They react with acids to form salts. That's what will happen here. Amino group, amine group hai, that means it will have a lone pair. It will act as a base. It is going to donate this lone pair to the proton over here of the acid, and you will get a salt. Fine. Similarly, aniline in presence of the acid will give anilinium chloride. You get salts whenever you make the amines to react with acids. Then these amine salts, on treatment with a base like sodium hydroxide, they regenerate the parent amine. So you want to get back now the parent amine, you will make it to react with OH negative of any strong base, say sodium hydroxide. Amine salts are soluble in water but insoluble in organic solvents like ether. This reaction is the basis for the separation of amines from the non-basic organic compounds insoluble in water. The reaction of amines with mineral acids to form ammonium salts shows that these are basic in nature. Amines have an unshared pair of electrons on nitrogen atom, due to which they behave as Lewis bases. That is, they can share an electron pair. Basic character of amines can be better understood in terms of their Kb and pKb values explained below. Now again, the very numerical part, K value, the constant of the reaction rate constant. What you do is basically you take the concentration of the products divided by the concentration of the gaseous reactants, and that's how you get for water. Again, you'll do the same and you'll get Kb value. So pKb we know is minus times log of Kb. Larger the value of Kb or smaller the value of pKb, stronger is the base. The pKb values of few amines are given. pKb value of ammonia is 4.75. Aliphatic amines are stronger bases than ammonia due to plus I effect of the alkyl groups, leading to high electron density on the nitrogen atom. जब हमारे पास aliphatic amines होते हैं, उनके पास hydrogen is replaced by plus I alkyl groups, जो plus I effect दिखाते हैं. As a high electron density you can find on the nitrogen atom. Their pKb values lie in the range of 3 to 4.22. Fine. So what you can see, if the pKb value is less, that means the Kb value is large. Alright. On the other hand, aromatic amines are weaker bases than ammonia due to the electron withdrawing nature of the aryl group. Aryl group is not electron donating. It's not like aliphatics. It is going to always withdraw the electrons. So that was all about the base dissociation constant values. The stronger the base, the larger will be the value of the Kb, the base dissociation constant. Or you can also relate it in terms of the smaller value of pKb, because Kb and pKb have an inverse relationship. Now moving on, we have... You may find some discrepancies while trying to interpret the Kb values of amines on the basis of plus I or minus I effect of the substituents present in amines. Besides inductive effect, there are other effects like solvation, steric hindrance, which affect the basic strength of amines. Just ponder over, you may get the answer. So basically it's trying to say that it depends upon what all other alkyl groups, with what do you replace the hydrogen in the ammonia. That is going to also depict the basic strength. And you know there are so many effects taking place. It's not just the electron donating or withdrawing effects. Structure basicity relationship of amines. Basicity of amines is related to their structure. Basic character of an amine depends upon the ease of formation of the cation by accepting a proton from the acid. So what basically the base does, the ease with which it can accept the proton, that is equivalent to basically donating an electron pair from the acid. The more stable the cation is relative to the amine, more basic is the amine. So what is the ease with which it can form the cation? That is the basicity. Alkane amines versus ammonia. So basically we'll see which is more basic. Let us consider the reaction of alkane amine. This is an amine and you have ammonia also over here. Alright, you have R group over here instead of one hydrogen. You have taken a primary amine and you've made it to react with H positive, any acid or anything that is basically positive in nature. Due to the electron releasing nature of alkyl group, the R basically it pushes electrons towards nitrogen, makes the unshared electron pair more available for sharing with the proton of the acid. Moreover, the substituted ammonium ion formed from the amine gets stabilized due to dispersal of the positive charge by the plus I effect of the alkyl group. Hence, alkyl amines are stronger bases than ammonia. So if we look at the reactant side and also the product side, both are stabilizing more stable, because see over here, if you have an alkyl group, I'm so sorry for the time lag in between. I don't know, something just happened to it. So where were we exactly? We are having it over here. The basicity, basically we were discussing the how do we depict the basicity of an amine. This basically depends upon what is the ease of the cation formation. And we saw in case of an amine, there's an electron donating group, there's an R group which is going to make the electrons even more available for the proton to attack on it, and then afterwards you again have this R group which is going to stabilize this positive charge on the nitrogen. So alkyl amines are stronger bases than ammonia. Thus the basic nature of aliphatic amines should increase with increase in the number of alkyl groups. This trend is followed in the gaseous phase. The order of basicity of amines in the gaseous phase follows the expected order. Like the tertiary amine will be more basic than the secondary one and the primary one. So this will hold true for gases only. This trend is not regular in the aqueous state, as is evident by their pKb value. So that's what it's trying to say. pKb values of the solutions, they're not going to depict the same. In the aqueous phase, the substituted ammonium cations get stabilized not only by electron releasing effect of the alkyl group, but also by solvation with water molecules. So whenever you take the aqueous state, what happens to the Kb values? They increase rapidly because solvation will also be a factor that is to be considered now. The greater the size of the ion, lesser will be the solvation and the less stabilized is the ion. The order of stability of ions are as follows. So we know the less the size of the ion, the more will be the solvation and more stabilized it will be. Decreasing order of extent of hydrogen bonding in water and order of stability of ions by solvation is given over here. So over here, this will be a larger ion. There will be a lesser solvation and as a result, lesser stability. So as a result, the tertiary amine will not be the most basic. Otherwise, over here, it will be the primary amine. And that is due to the similar solvation reason. Greater is the stability of the substituted ammonium cation, stronger should be the corresponding amine as a base. तो obviously जितना stable हमारा product होता है उतनी ज़्यादा reaction favor होती है. Thus the order of basicity of aliphatic amines should be primary, then secondary and then tertiary, which is opposite to the inductive effect based order. Secondly, when the alkyl group is small like CH3 group, there is no steric hindrance to hydrogen bonding. In case the alkyl group is larger, bigger than CH3 group, there will be steric hindrance to hydrogen bonding also. Therefore, the change of nature of the alkyl group, example from CH3 to C2H5, results in change of the order of basic strength. Thus, there is a subtle interplay of the inductive effect, solvation effect and steric hindrance of the alkyl group, which decides the basic strength of alkyl amines in the aqueous state. Very important. So in the gaseous state, we saw it was very easy. All we had to look at was the ease with which the cation was being formed, and that was basically dependent upon the inductive effect, electron donating effect, which increased as we went from primary to secondary to finally the tertiary amines. But what happens in case of aqueous amines? We take in consideration the solvation as well as the steric hindrance to hydration that the alkyl groups attached to the nitrogen atom would be providing. So that also will be taken in consideration over here. The order of basic strength in case of methyl substituted amines and ethyl substituted amines in aqueous solution, of course they're going to differ because ethyl and methyl, till methyl it's fine, it's not going to provide so much of steric hindrance, but ethyl definitely will. So aryl amines versus ammonia. Now let's come to aryl amines, basically the amines which are containing an aromatic group along. Now pKb value of aniline is quite high. Why is it so? It's because in aniline or other aryl amines, the NH2 group is attached directly to the benzene ring. And when it's directly attached, what happens is, it's an OP director. We know the lone pair on the nitrogen, right? It results in the unshared electron pair on nitrogen atom to be in conjugation with the benzene ring, because there is lone pair pi conjugation and thus making it less available for protonation. The conjugation is a very stabilizing effect. Mesomeric effect will take place. So you'll get all the resonating structures over here, finally a resonating hybrid. So this electron pair is not available for any of the protons or any cation formation now, because it's already entered into the process of resonance. So you have you'll find aniline is in resonance. It's a resonance hybrid of the following 5 structures. On the other hand, anilium ion obtained is obtained by accepting a proton, can have only 2 resonating structures. All right, you can see only 2 resonating structures, even if it has gotten converted into the cation. And we know the greater the number of resonating structures, greater will be the stability. Thus you can infer that aniline is more stable than anilium ion, hence the proton acceptability or the basic nature of aniline or other aromatic amines would be less than that of ammonia. In case of substituted aniline, it is observed that electron releasing groups like OCH3, CH3 increase basic strength, whereas electron withdrawing groups like NO2, SO3H, COOH and X decrease it. So we know this has already been taught what are the electron releasing groups and what are the electron withdrawing groups. So whenever you have electron releasing groups, they increase the basic strength, all right, and if you have electron withdrawing groups, they're going to decrease the basic strength. All right, now you have alkylation, another the second very important chemical reaction. Amines undergo alkylation on reaction with alkyl halides, in which we actually know that reaction is nucleophilic aliphatic substitution of the halide, and the reaction product is a higher substituted amine. Then similarly we have acylation. Aliphatic and aromatic primary and secondary amines react with acid chlorides, anhydrides and esters, all of these, by nucleophilic substitution reaction. This is known as acylation. You can consider this reaction as the replacement of hydrogen atom of NH2 or NH group by the acyl group. Alright, so acylation means replacement of hydrogen atom by acyl group. The products obtained by acylation reaction are known as amides. The reaction is carried out in the presence of a base stronger than the amine, like pyridine, which removes the HCl so formed and shifts the equilibrium to the right hand side. So Lee-Chartier's principle applies over here also. You have any ethanamine, any amine you've taken, you take a very strong base which can take out the HCl later on, and then you have amides being formed. Alright. So this lone pair is attacking on this acyl group on the carbon, which has positive charge over here, and this is having a negative charge. We know why, because there's oxygen, there's electronegativity difference. Then we have in the presence of base, what is happening now? This H is coming out for the base, and you have an O negative over here. And since N is getting connected to this carbon, it will have a positive charge. Then this hydrogen is going to come out because nitrogen is highly electronegative and it cannot stabilize a positive charge on it, and that's how you get an amide. Similarly, you give another examples also. Amines also react with benzoyl chloride. This is known as benzoylation. So you take an amine, you take benzoyl chloride. So this is basically the benzoyl chloride, and then you get amide, benzene amides. What do you think is the product of reaction of amines with carboxylic acids? They form salts with amines at room temperature. Alright, because they're acidic in nature, amines are basic. Carboxylic acid with amines will give salts. Now, carbyl-amine reaction. Aliphatic and aromatic primary amines on heating with chloroform and ethanolic potassium hydroxide form isocyanides or carbyl amines. So it's one and the same thing. Alright, which are foul-smelling substances. Secondary and tertiary amines do not show this reaction. This reaction is known as carbyl-amine reaction or isocyanide test, and is used as a test for primary amine. So you take a primary amine, aliphatic or aromatic, whatever, and you heat it with chloroform, CHCl3, and ethanolic potassium hydroxide, KOH, which is a base. And you're going to get cyanides, isocyanides or carbyl-amines, one and the same thing, and potassium chloride and water as byproducts. Then coming to reaction with nitrous acid, HNO2. Nitric is HNO3. Three classes of amines react differently with nitrous acid. Alright, we have primary ones, and then primary aliphatic amines react with nitrous acid to form aliphatic diazonium salt. So N positive, Cl negative. This is basically your diazonium salt, which are being unstable, liberate nitrogen gas quantitatively and alcohol. So alcohols you get and nitrogen you get. Quantitative evolution of nitrogen is used in estimation of amino acids and proteins. So that's how you identify whether you've taken an amine, you've taken a protein, when you get nitrogen gas at the end. On reacting this amine group with nitrous acid, fine, you will get diazonium salt. वो unstable होता है, it is going to release alcohol and nitrogen gas. Then you have aromatic amines react with nitrous acid at low temperatures to form diazonium salts. Again, a very important class of compounds used for synthesis of a variety of aromatic compounds. So whenever you get benzene diazonium chloride, it's very much stable. It's going to be as it is. Whenever you make the aniline to react with the same nitrous acid and all the presence of NaNO2 and HCl, temperature also, and you'll get a diazonium, benzene diazonium salt. Secondary and tertiary amines react with nitrous acid in a different manner, which has not been discussed here. Alright, reaction with aryl sulfonyl chloride. Benzene sulfonyl chloride, this C6H5SO2Cl, this is basically sulfonyl chloride of benzene, is also known as Hinsberg's reagent, very important. Reacts with the primary and secondary amines to form sulfonamides. So if you want to get sulfonamide, you'll react with the primary and secondary amines like this, okay? You are given a primary amine over here and you'll get benzene sulfonamide. Alright, so which is a soluble in base. The hydrogen, the reaction of benzene sulfonyl chloride with primary amine yields N-ethyl benzene sulfonyl amide. Now the hydrogen attached to nitrogen in sulfonamide is strongly acidic due to the presence of strong electron withdrawing sulfonyl group. Hence it's soluble in alkali. Why? It can give out hydrogen very easily. This is a really strongly electron withdrawing group. Then we have in the reaction with secondary amine, N-diethyl benzene sulfonamide is formed. So if you take a 2-degree amine, a secondary amine, you will get diethyl substitution over here. So in presence of a hydrogen again, you will have the R group which was here in the amine. Then we have, since N,N-diethylbenzene sulfonamide does not contain any hydrogen atom attached to nitrogen, it is not acidic. Hence, it's insoluble in the bases. Of course, if there's no hydrogen, then it will not be acidic at all, and it cannot dissolve in bases. Tertiary amines do not react with benzene sulfonyl chloride. This property of amines reacting with benzene sulfonyl chloride in a different manner is used for the distinction of primary, secondary, and tertiary, and for the separation of a mixture of amines. However, these days benzene sulfonyl chloride is replaced by para-toluene sulfonyl chloride also. So you can see there was a difference in reaction with these sulfonyl chlorides with primary, secondary, and tertiary amines. So tertiary ones don't even react. So that's how you can actually separate them, and you can demarcate, you can identify which of the amine you have taken. So electrophilic substitution, you've read earlier that aniline is a resonance hybrid of 5 structures. Where do you find the maximum electron density? We know orthopara because NH2 is an OP director. Thus NH2 is orthopara directing in a powerful activating group. So first we have bromination. Whenever you have to do electrophilic substitution, you need to have an OP director, so you have it right now. You are doing bromination now, and 2,4,6 tribromoaniline you'll get. Fine, bromine water at room temperature to give a white precipitate of this. The main problem encountered during electrophilic substitution reactions of aromatic amines is that of their very high reactivity. Substitution tends to occur at ortho and para. If you have to prepare mono-substituted aniline derivative, how can the activating effect of NH2 be controlled? Of course, you'll take a deactivating group. This can be done by protecting it by acetylation, that's another way, with acetic anhydride, then carrying out the desired substitution followed by hydrolysis of the substituted amide to the substituted amine. What happens is basically this is a really explosive reaction. Aniline is a very reactive compound, and it will react explosively with bromine, and you'll get this. So if you only want to get a mono substituted aniline, you will take acetyl group along. Fine, आप acetyl लेंगे, so that is going to control the reaction. Fine, there is not going to be such an activating group. This is minus. This is going to also take in some amount of electrons from here also. Then what happens is this we get as a product. This is the major product, the para one, and finally in presence of acidic or basic medium, you'll get the amine back from the amides. The lone pair of electrons of nitrogen of acetanilide interacts with oxygen atom due to resonance as shown below. So here we go. We have the lone pair of nitrogen coming here, this pair of this bond going there, and the arrows are showing it. I'm not going to mess this diagram more. So this will get a positive charge, and here you have a negative charge. This is resonance. All right. Okay. Hence, the lone pair of electrons of nitrogen is less available for donation to benzene ring now by resonance. Therefore, activating effect of NHCOCH3 group is less than that of amino group. So, what was the reason we took acetyl over there? That's been explained over here. Because what happens is the electron donating effect of nitrogen is decreased because of resonance. Now, the negative charge is all here. So, when this is happening, you'll have a lesser activating effect of amine group. Now you have nitration. Direct nitration of aniline yields tarry oxidation products in addition to the nitro derivatives. Moreover, in the strongly acidic medium, aniline is protonated to form the anilium ion, which is meta-directing. That is why besides the ortho and para derivatives, significant amount of meta-derivative is also formed. So what happens over here? Nitration can be done directly. We know HNO3, H2SO4, 288 Kelvin. These are all the requirements. And if you have a strongly acidic medium, what will you do? Aniline, it will be protonated to form the anilium ion. Anilium ion we know is meta-directing because it has a positive charge in it. So you'll also get some amount of meta product. Although this is an ortho-para directing group, but if you put this in an acidic medium, proton is going to come here. And if you get an anilium ion, it becomes a meta-directing group. However, by protecting the amine group by acetylation, again, with acetic anhydride, nitration can be controlled and the para nitro derivative can be obtained as the major product. So you don't want any meta compound. So karne ko hum kuch bhi kara sakte. You've taken now here acetyl group and you'll only get para as the major compounds. Coming to sulfonation, again H2SO4 ke presence mein aniline reacts with concentrated sulfuric acid to form anilinium hydrogen sulfate, which on heating with sulfuric acid produces para-aminobenzene sulfonic acid. This is the intermediate that has been formed, and finally on heating you'll get sulfonilic acid. Alright, on the para position you'll have the sulfonic group, and this will be in resonance with this. Fine. which is known as sulfonilic acid. Para-aminobenzene, sulfonic acid is also known as sulfonilic acid. This will be the major product. Zwitter ion will also be formed in the aqueous solution. Aniline does not undergo Friedel-Crafts reaction, alkylation or acylation due to salt formation with aluminium chloride, the Lewis acid, which is used as a catalyst. So you're taking catalysts. We know it's anhydrous AlCl3 and all of the rest of the things, but this doesn't undergo any Friedel-Crafts reaction because it will form salt. Due to this, the nitrogen of aniline acquires a positive charge, hence it will act as a strong deactivating group, so it cannot go for further reaction, becomes a deactivating group. Now, very important is again diazonium salt. They have the general formula Rn2 plus X minus, fine, where R stands for an aryl group, alright. X negative may be chlorine, bromine, HSO4 negative, BF4 negative, etc. They're named by suffixing diazonium to the name of the parent hydrocarbon from which they are formed. You just add a suffix of diazonium and you're done with the nomenclature. Followed by the name of anions such as chloride, hydrogen sulfate, etc. Whatever anion you are taking over here in presence of this X. The N2 positive group, this is called the diazonium group. For example, this, you're given an example. This is named as benzene. The parent chain carbon, it's benzene only, diazonium, the N2 plus, it's the diazonium, and chloride will be the anion, fine. And this will be similarly benzene, diazonium, hydrogen sulfate, depending upon कि हमारा हमने कौन सा जो last पे anion है वो लिया है और हमारा parent chain क्या है. Diazonium will remain there. N2 positive is always present. All right. Primary aliphatic amines form highly unstable alkyl diazonium salts. Primary aromatic amines form arene diazonium salts, which are stable for a short time in solution at low temperatures. Stability of arene diazonium ion is explained on the basis of resonance again. So you have aryl group over here. This is the diazonium salt, N2 positive, and over here you can see it is in a state of conjugation. So there's resonance, and that's how it's stabilized. Now, what is the method of preparation of diazonium salt? Benzene diazonium chloride is prepared by the reaction aniline with the nitrous acid at 278 Kelvin. Nitrous acid is produced in the reaction mixture by the reaction of sodium nitrite and hydrochloric acid. Conversion of primary aromatic amines into diazonium salts is known as diazotization. So if you take a primary amine, you convert it into diazonium salt, you call this process diazotization. Due to its instability, the diazonium salt is not generally stored and is used immediately after its preparation. So its instability. Physical properties. Benzene diazonium chloride is a colorless crystalline solid. It's readily soluble in water, stable in cold but reacts with water when warmed. It decomposes easily in the dry state. Benzene diazonium fluoroborate is water insoluble and stable at room temperature. Otherwise, it's generally soluble, and in cold water, it's stable more or less, but it'll react with warm water. Coming to the chemical reactions, the reactions of diazonium salt can be broadly classified into reactions involving displacement of nitrogen and reactions involving retention of diazo group. Either you displace nitrogen or you retain the diazo group. Let's see, reactions involving displacement of nitrogen. Diazonium group, being a very good leaving group, is substituted by other groups such as chlorine, bromine. Ye sare anions, they can replace diazonium because it's a very good leaving group which displace nitrogen from the aromatic ring. The nitrogen formed escapes from the reaction mixture as a gas. So the first is replacement by a halide or cyanide ion. So chloride, bromide, cyanide nucleophiles can easily be introduced in the benzene ring in the presence of copper ion. This reaction is called Sand-Mayer's reaction. So in Sand-Mayer's reaction, you bring in any of the nucleophiles, any of the ions, and you introduce them into the benzene ring, alright, in the presence of copper via the Sand-Mayer's reaction. Then alternatively, chlorine or bromine can also be introduced in the benzene ring by treating the salt solution with corresponding halogen acid in the presence of copper powder, and that is Gattermann reaction. Gattermann में हम क्या करते हैं? We'll take the chlorine, bromine, and we'll treat the diazonium salt with the halogen acid of this chlorine, bromine acid, all right, in the presence of copper powder again. So that's how you convert the salt into your simple aryl halide and nitrogen, and copper halide you get as a byproduct. The yield in Sand-Mayer reaction is found to be better than Gattermann reaction. Now replacement by iodide. Again, you can have iodine is not easily introduced into the benzene ring directly, but when diazonium salt solution is treated with potassium iodide, normally iodine ऐसे enter नहीं करेगा, but if you treat this ammonium salt with potassium iodide, you'll get iodobenzene. Then replacement by fluoride. In all these reactions, what are we doing? Basically, we are displacing the diazonium group, the azonium group with any of the anions, and by treating them with various reagents. So that is displacement. When arene diazonium chloride is treated with fluoroboric acid, which is HBF4, arene diazonium fluoroborate, this is precipitated, which on heating decomposes to yield aryl fluoride. Replacement by hydrogen. Certain mild reducing agents like hypophosphorus acid or phosphenic acid or ethanol reduce diazonium salts to arene. So you can even reduce reduction, and themselves get oxidized to phosphorus acid and ethanol respectively. So you can reduce it. Replacement by hydroxyl group. If the temperature of the diazonium salt of solution is allowed to rise to this, the salt gets hydrolyzed to phenol. So this is your salt. You can hydrolyze it. The hydroxyl group will replace this N2Cl group. Then we have replacement by NO2 group, the nitro group. When diazonium fluoroborate, alright, fluoroboric acid, this is diazonium fluoroborate, is heated with aqueous sodium nitrite, alright, solution in the presence of copper, the diazonium group is replaced by nitro group. So this is another displacement. Now you have retention of diazo group. Now if you're not removing the diazo group, if you're not removing the nitrogen, you're still retaining that. We have various reactions, and we have coupling reactions is given. The azo products obtained having have an extended conjugate system having both the aromatic rings joined through N double bond N. So this is what happens in the in these reactions, in coupling reactions. Both the aromatic rings will be joined through N double bond, and you can see over here also. These compounds are often colored and are used as dyes. Benzene diazonium chloride reacts with phenol, in which the phenol molecule at its para position is coupled with the diazonium salt to form para-hydroxyazobenzene. This type of reaction is known as coupling reaction. Similarly, the reaction of diazonium salt with aniline yields para-aminoazobenzene. This is an example of electrophilic substitution reaction. So what happens is, even when you have your alcoholic group over here, it will be coupled with N double bond N. So there will be retention of the N nitrogen atom present over there. It won't be replaced as in the previous case that we did already. Then this is para-hydroxy azobenzene, which is an orange dye, and this is para-aminoazobenzene if you treat aniline with diazonium salt. All right. Now we have importance of diazonium salts in synthesis of aromatic compounds. From the above reactions, it's clear that the diazonium salts are very good intermediates for the introduction of FCl, Br, I, Cn, OH, NO2 groups into the aromatic ring. You can easily make them enter by replacing the nitrogen atom. Aryl fluorides and iodides cannot be prepared by direct halogenation. The cyano group cannot be introduced by nucleophilic substitution of chlorine and chlorobenzene, but cyanobenzene can be easily obtained from diazonium salts. That's how you prepare organic compounds with the help of diazonium salts only. Thus, the replacement of diazo group by other groups. Alright, it's a very helpful reaction in preparing those substituted aromatic compounds which cannot be prepared by direct substitution. जहाँ आप directly benzene को substitute नहीं कर पाएंगे, वहाँ हम azonium salts का use करते हैं. That is, हम diazonium salt ले लेते हैं. When that is formed, it can be easily replaced by any of the anions that are given. And with that, we come to an end of the lesson. I hope it was useful, helpful in any sense. Thank you for watching, and I'll see you in my next one.